Okay, so you've applied GD&T, you've analyzed the stack-ups, and you've definitely mastered composite tolerancing. But as we dive into this explainer for the Advanced GD&T Masterclass, we're literally crossing the threshold into the absolute deepest levels of geometric precision.
Because right here is the ultimate unresolved question, the one that almost no engineer can answer confidently. How does a CMM software actually decide, mathematically, whether a part passes or fails, down to the geometry itself? To answer that, we are stepping into the advanced tier. Now, this completely assumes you've already finished both the beginner and intermediate tiers. That's 24 lessons covering the 14 symbols, datums, modifiers, virtual condition, composite position, and stack-up analysis. If you haven't finished those yet, no worries, but definitely review that material first because this tier builds directly on top of all of it.
In this explainer, we're tackling some incredibly high-stakes global consequences. We'll start with the complex clash between ASME Y14.5 and ISO GPS when it comes to global sourcing. Then we're going to leave simple, linear math entirely behind and plunge straight into the raw computational power of full 3D Monte Carlo simulation.
We'll also be confronting the rigid traditional requirements of geometric dimensioning and stacking them up against the wild, kinda unpredictable new frontier of additive manufacturing.
And ultimately, we're going to uncover the raw mathematical definitions hidden underneath every single feature control frame you have ever read. And once you've conquered all this material, well, the Expert Mastery tier is coming up soon. That's where this stops being just about technical depth and starts being about truly leading, certifying, and owning GD&T at an organizational level. So definitely subscribe so you don't miss out on that.
All right, the stakes are set. Let's jump straight into Lesson 1. ASME Y14.5 and the consequences of global sourcing.
All right, picture this. It's the exact kind of scenario that keeps quality managers staring at the ceiling at 3 a.m. You're a highly capable US-based supplier. A European aerospace client sends over a standard PDF print. You look at the GD&T symbols, and hey, they look perfectly familiar, right? So you program the CNCs, you machine 1,000 parts, your inspection team proudly signs off on the whole batch, and you ship them out. But then, the client gets the batch and literally scraps the entire production run. No way, right? Why did that happen? Well, because while that print looked absolutely identical to the ASME standard you know and love, it was actually operating on a fundamentally different default assumption. Welcome to Lesson 1 of our Advanced GD&T Masterclass. In this explainer, we're diving deep into the critical differences between ASME Y14.5 and ISO GPS. Because honestly, knowing your defaults is pretty much the only thing standing between a perfect part and a total disaster.
So, let's say I hand you a print with a simple tolerance feature. Maybe it's a pin, with a diameter dimension and a basic straightness callout. How do you interpret that? If you're coming from the ASME world, you're automatically going to apply the envelope principle and RFS, regardless of feature size. That's just muscle memory. But if that exact same print was authored under ISO GPS, that assumption is completely wrong. ISO uses the independency principle by default. So, without explicitly knowing which standard governs the document, you literally cannot know what the print is actually asking you to make or inspect. It's wild.
This perfectly highlights the core problem we're dealing with here. Think about it like this. Same symbols, different default assumption. So which region are you actually looking at? It really helps to think of GD&T as a language. ASME and ISO GPS, they're kind of like American and British English. They use the exact same alphabet, and I mean 90% of the vocabulary overlaps perfectly, but the slang, the underlying grammar rules, they can completely invert the meaning of a sentence. Identical symbols mean entirely different things depending on the region and the governing standard.
Now, because the ISO GPS system is spread out across literally dozens of distinct, constantly updating documents, we really need a solid anchor of certainty for this explainer. And for us, that anchor is the heavily documented ASME Y14.5-2018 standard. While this is technically an international standard governed by the American Society of Mechanical Engineers, its historical roots are distinctly US-based. So throughout this masterclass, we're going to plant our feet firmly in these well-documented ASME rules and use them to provide a really accurate, high-level contrast against the European-born ISO GPS system. Okay, so let's break down the great default divide. This is the baseline knowledge every single global supply chain engineer just has to commit to memory. Under ASME Y14.5, your default is the envelope principle. You probably know it as rule number 1. This means the limits of size dictate the extreme variations of form allowed. Perfect form is required at maximum material condition, right? But flip over to ISO GPS, and the default is the independency principle.
Form and size are treated completely independently unless you specifically go out of your way to add a modifier symbol, like the circle D, to invoke an envelope requirement. If you assume an envelope exists on an ISO print where it wasn't specified, well, you're just over-constraining your manufacturing process and basically throwing money down the drain.
To really anchor the ASME side of things, let's look at how the source text rigorously defines this. If we look at Section 5.8 of ASME Y14.5, it outlines the limits of size. It defines the tolerance as the total amount of dimension or features permitted to vary, and crucially, it establishes the boundary conditions. Under ASME, unless otherwise specified, the limits of size prescribe a perfect geometric boundary at MMC that the feature absolutely cannot violate. This is your default U.S. manufacturing assumption, hard-coded directly into Section 5 of the standard.
So how does all this actually play out when you're reading a feature control frame? Well, when an American machinist reads an ASME feature control frame without any material modifiers, they correctly read it as RFS, regardless of feature size. But if that exact same frame shows up on an international print, that requires an immediate double check. ISO has a completely different library of modifiers and defaults. As a global supply chain engineer, you can never, ever assume defaults are universally interchangeable. A simple position callout means one thing in Detroit and potentially something completely different in Munich if the standards aren't strictly mapped out.
And the tricky part? The differences definitely don't stop at just size and form. We also have to do a bit of lexicon translation. Take Section 7.5 of ASME Y14.5, for example. It defines a true geometric counterpart as the theoretical perfect boundaries or surfaces used to establish a datum reference frame. It's a beautifully rigorous definition. But, just like stepping off a plan in a foreign country, if you confidently drop the phrase true geometric counterpart in an ISO-dominant facility, you are going to get nothing but blank stares. ISO GPS uses completely different terminology for its datum simulators and associated theoretical boundaries.
Building those translation bridges is absolutely crucial. ASME relies super heavily on true geometric counterpart in Section 7.5 and strictly details degrees of freedom constraints, translation and rotation, over in Section 7.2. Meanwhile, the ISO side requires a whole different vocabulary for datum feature simulators and constraint logic. And to top it off, the symbol sets themselves have distinct additions. ISO has very specific symbols for things like the independency principle or dynamic profiling that either look totally different or just straight up don't exist in the same way in the ASME ecosystem. You can't just read the shapes anymore, you literally have to know which dictionary they came from.
All right, let's switch gears for a second. Time for a quick pop quiz to keep you on your toes. Imagine you're looking at an actual adoption notice, tucked away in the title block or the general notes of a fresh engineering drawing you just received. It mentions the Department of Defense, Picatinny Arsenal, and it explicitly calls out ASME Y14.5 adopted on 9 February 2009.
So based on that little slice of title block information, here is my question for you. Which standard governs this print? And practically speaking, what does that actually mean for our default interpretation of every single dimension on that page? Take a second and really think about it. Before any metal is cut, before any CMM is even programmed, what is the rule of the land here? Got your answer? Okay, here it is. Because the drawing explicitly references ASME Y14.5, you have absolute confirmation. The envelope principle applies. Perfect form at MMC is required, and RFS applies to all unmodified geometric tolerances. The big takeaway here? You must always, always verify the exact governing standard and addition noted on the print itself. Never guess based on where the customer's headquarters is located. An aerospace firm in France might author an ASME print for a U.S. defense contract, right? And a U.S. automaker might easily author an ISO print for a European subsidiary. Always check the title block.
All right, so we are moving into the practical application phase of this explainer now. Knowing the theory and the history behind these standards is great, but how do we actually protect our manufacturing margins in the real world? Well, it all boils down to one simple, absolutely non-negotiable step before you ever accept a contract. There is one single, crucial question you have to put in every supplier RFQ.
And here it is. You literally want to copy and paste this exact phrasing into your request for quote documentation. Which specific GD&T standard and edition governs the default interpretations on this print? That's it. If the drawing title block is missing this information, or if it ambiguously just says tolerances apply, kick it right back to the design engineer. Do not accept the liability of guessing. Forcing the client to specify ASME Y14.5 2018 or the applicable ISO GPS matrix standard is the absolute best way to guarantee that this ambiguity never costs you a scrapped production run. So now that we've nailed down the baseline standard defaults and exactly how to legally lock them down on our prints, it's time to bridge into what comes next. Lesson 1 has been all about manual interpretations, worst-case scenarios, and the foundational rules of ASME versus ISO. But hey, modern manufacturing doesn't stop at manual math on a scratch pad. The next evolution is moving way beyond 2D paper defaults and diving straight into the world of full computational 3D tolerance analysis, where we feed these exact rules into software to simulate thousands of assemblies before a single prototype is even made.
Which brings us to the end of today's explainer and leaves you with one final provocative question to chew on. Are you ready to simulate true 3D tolerance stack-ups? Now that you fully understand how these defaults can completely alter a part's boundaries, imagine calculating that complex geometry across a 50-part assembly. You're going to want to join me in Lesson 2, where we'll transition your mindset from manual blueprint reading toward advanced computational 3D simulations. It's going to be a real game changer, and you won't want to miss it.
We're moving from 1D math into the absolute powerhouse of 3D prediction. We'll be diving into 3D tolerance stack-up simulation, zeroing in on Monte Carlo methods and tolerance analysis software. This right here is where all that theory you've learned finally meets the complex reality of modern manufacturing.
Look, we all know the absolute frustration of doing a manual 1D worst-case chain that promises a perfect fit on paper. You do the math, it checks out, but then you get to the shop floor, put the parts together, and boom, interference. Why does this happen? Well, it's because real-world variation happens in 3 dimensions, not just one. When parts actually made, they don't just sit perfectly flat. They twist, they tilt, they shift across multiple planes. A single straight line of math literally can't account for what's happening in a real volumetric assembly.
Take a look at an incredibly complex 3D assembly like the one we're showing here. When you compare a simple 2D chain to something with dozens of contributing dimensions, overlapping X, Y, and Z planes, and multiple load paths all crashing together on one critical gap, you really have to ask yourself, could you even build the equation for this by hand? The honest answer? No way. Or at least, not without making so many wild assumptions that your final answer is basically useless. The complexity completely traps you. You just can't build this by hand and expect reliable predictability.
This comparison really highlights exactly where traditional methods just fall apart. The ASME Y14.5 standard, specifically Appendix I2.1, actually warns us about tolerance accumulation ambiguity when we don't have a clear origin or measurement vector. Basically, if a tolerance is just slapped onto a location dimension between surfaces, you don't have an assumed origin, and that breaks down fast in complex assemblies. But 3D computational analysis, it solves this entirely. It locks everything to perfect theoretical datum reference frames. It handles all those multiple X, Y, and Z planes, automatically calculates those tricky rotational contributions, and captures the nonlinear geometric relationships that a 1D straight-line calculation completely ignores.
Section 1. Enter Monte Carlo simulation. Let's see how this statistical powerhouse actually works.
So, at its core, the Monte Carlo simulation is a tool that rapid-fires randomly sampled virtual builds. Here's how it plays out in 4 simple steps. Step 1, the software reads the tolerances you've applied to your CAD models. Step 2, it randomly samples dimensions from within each part's tolerance range based on assumed statistical distributions, like a classic normal bell curve. Step 3, it mathematically simulates a virtual build of those specific, slightly imperfect parts. And step 4, it repeats this entire process 10,000 times, or even more, in literally a matter of seconds. You're basically manufacturing a production run of 10,000 assemblies inside the computer, predicting the exact statistical outcome before a single piece of metal is ever cut.
This really shows why computational power is an absolute game changer. A Monte Carlo simulation captures those nonlinear geometric relationships and multipath load effects that a basic manual RSS, the simple square root sum of squares formula, just can't handle. See, RSS assumes a lot of independence and linearity. But in reality, a tiny rotation on a primary datum plane is going to amplify a translation way out on a tertiary feature. Monte Carlo software calculates all of those rotational contributions across planes simultaneously, giving you a highly accurate map of exactly where your assembly might fail.
Section 2. Feature control frames. The simulation's DNA.
Now here's absolutely the most crucial point to understand. All of this advanced software, it is completely blind without perfect geometric inputs. The exact same feature control frames, datums, and modifiers that you've been studying are the literal DNA feeding the software. It reads that rectangular box left to right, it checks the geometric characteristic symbol, grabs the tolerance value, checks for a diameter symbol to see if it's a cylindrical zone, factors in any maximum material condition modifiers, and, most importantly, anchors the whole simulation using the datum references in their exact order of precedence. Those primary, secondary, and tertiary datums are what tell the software exactly how to constrain the degrees of freedom for every single one of those virtual builds.
It all boils down to that classic engineering mantra: garbage GD&T in, garbage simulation out. A single bad feature control frame, a forgotten diameter symbol, or a misunderstood datum reference frame is going to completely skew your entire result. Say you reference a datum feature out of functional order. The software will still happily run 10,000 builds, sure, but it's going to constrain the virtual parts incorrectly. So your input quality is absolutely paramount. All that symbol-level knowledge you've mastered is exactly what makes these advanced tools work.
And keep in mind, this isn't just some software magic acting outside the standard rules. It's grounded right there in ASME Y14.5. Section 3.60 defines statistical tolerancing as the assigning of tolerances to related components of an assembly on the basis of sound statistics. The standard explicitly says that features identified with statistical tolerancing should be produced with statistical process controls. So this 3D software is quite literally bridging the gap between your design intent and the cold, hard statistical realities of the manufacturing floor. Section 3. Reading statistical defect rates. Let's look at what the software actually tells us. Okay, so how do we actually interpret the output of those 10,000 virtual builds? Take a close look at this simulated outcome distribution. This is a classic Monte Carlo output histogram for our critical assembly gap. That big center mass right in the middle shows where the vast majority of our virtual builds landed. But look way over at the upper tail, that bright red defect zone where the gap gets too tight or interference happens. Before I give you the answer, just based on the shape and spread of this histogram, what would you estimate the predicted defect rate is for this assembly? Just guess a percentage in your head right now. Got it?
The software spits out a highly specific 4.2% defect rate. Think about that for a second. Instead of a manual worst-case analysis giving you this binary, stressful, it fits or it doesn't answer, which usually just forces you to use overly tight, insanely expensive tolerances to cover yourself, the computational analysis gives you actionable statistical reality. You might look at a 4.2% defect rate and say, you know what? Loosening a tolerance and saving thousands of dollars in machining is absolutely worth dealing with a 4% scrap rate. It completely empowers you to make strategic business and engineering decisions based on solid data rather than fear.
Section 4. The next frontier. Additive manufacturing.
You really need to master this computational mindset, because 3D tolerance analysis is absolutely no longer a luxury. It is the required baseline for where advanced engineering is heading next. And that brings us to a massive question for the future. How do our foundational tolerancing assumptions shift when 3D printing removes traditional machining constraints entirely? I mean, when a part is grown layer by layer instead of being cut away by a spinning tool, the very rules of physical assembly and statistical variation are completely rewritten. So you'll definitely want to join us in Lesson 3 to find out exactly how GD&T applies to additive manufacturing and how you can stay ahead of the curve. Keep learning, and I'll catch you in the next explainer.
So how do you actually guarantee that a part designed in New York is going to perfectly fit a component machined all the way over in Tokyo? It's a massive challenge in modern global manufacturing. Think about it. If an engineer models a perfectly cylindrical pin on their computer and a machinist on the other side of the planet cuts it out of solid metal, their real physical part is never going to be completely perfect. It's going to have microscopic bends, warps, and size variations. So how do we make absolutely sure those tiny imperfections don't lead to a catastrophic failure during assembly? Well, we do it by using a universal, incredibly precise visual language.
Welcome to this explainer. Today, we are decoding the absolute blueprint of reality, the ultimate engineering standard that makes the modern physical world possible, ASME Y14.5. This isn't just a set of polite suggestions, guys. It's the definitive rulebook for geometric dimensioning and tolerancing, or GD&T. By the end of our time together today, you're going to understand the core logic that transforms a purely theoretical blueprint into a functional physical reality.
Here is our roadmap for today. We'll be looking at the Y14.5 standard, rule number 1, datum reference frames, constraining degrees of freedom, and feature control frames. Let's jump right in. Section 1, the Y14.5 standard. Now, ASME Y14.5 is an internationally recognized standard. Governed by the American Society of Mechanical Engineers, this is quite literally the law of dimensioning and tolerancing, and we'll be focusing specifically on the 2018 revision today. This standard establishes the exact symbols, definitions, and rules for stating requirements on engineering drawings and digital data files. It leaves absolutely zero room for guesswork. When a drawing references the standard, it is legally binding the manufacturer to these exact, unyielding definitions. Moving right along to Section 2, Rule number 1, the envelope principle. Okay, the envelope principle. It might sound kind of academic, but it's actually incredibly intuitive. It dictates that the form of an individual regular feature of size is inherently controlled by its limits of size. I want you to literally imagine an invisible box or a perfect cylinder floating in space. This envelope defines the absolute boundary that a physical part simply cannot violate. If you design a peg to fit into a hole, this rule ensures the peg doesn't bend so much that it gets stuck, even if its diameter is technically within tolerance. Now look at the exact phrasing straight from the ASME standard itself. It states that the surface shall not extend beyond an envelope of perfect form at maximum material condition, or MMC. MMC is just the point where a part contains the most amount of material allowed by its size tolerance. Think of the absolute largest allowable pin or the smallest allowable hole. Rule number 1 says that if the part is manufactured at this maximum limit, it must be geometrically perfect in form. No bending, no tapering allowed. It must fit perfectly into that theoretical gauge. But here's the thing. While this perfect form envelope is the default law of the land, the standard is actually super practical. There are specific methods to override rule number 1, when perfect form at MMC just isn't functionally required for the part's end use. I mean, sometimes you just need a piece of stock metal to be a certain thickness, and you really don't care if it's slightly bowed. The standard provides specific geometric tools and notes to remove this envelope requirement, which can save immense amounts of time and money in manufacturing. Which brings us to Section 3, Datum Reference Frames. You see, you can't just measure a part willy-nilly. You have to establish a strict coordinate system. We do this by referencing specific features on the part in a very specific hierarchy: primary, secondary, and tertiary. This sequence tells the machinist and the quality inspector exactly how to place the part into their measurement equipment. Datums aren't just theoretical lines on a computer screen. They serve as the exact physical origin for all geometric relationships and tolerances on a blueprint. They literally represent the mating surfaces of how the part will eventually function in its final assembly. If a bracket mounts to a wall, the flat back of that bracket is going to be your primary datum. Everything else, every single hole, every slot, every edge, is positioned relative to that specific origin. All right, Section 4, Constraining Degrees of Freedom. Any unconstrained part floating in three-dimensional space has exactly 6 ways it can move. It has 3 translational degrees of freedom, meaning it can slide back and forth along the X, Y, and Z axes. And it has 3 rotational degrees of freedom. It can pitch, yaw, and roll, which the standard refers to as U, V, and W. To properly measure a part, you have to systematically strip away all 6 of these freedoms until the part is totally, completely locked down. And this perfectly illustrates how our primary, secondary, and tertiary datums lock down those specific degrees of freedom step by step. Imagine placing our part onto a flat surface plate. That flat plate acts as the primary datum, immediately killing 3 degrees of freedom. It can no longer translate down through the table, and it can't pitch or roll. Pushing it against the secondary rail kills 2 more degrees. Finally, sliding it against a tertiary block stops that last rotational degree of freedom. Boom, it is now completely locked in space. But wait, here is a massive conceptual hurdle that so many people miss. The physical part itself is not the datum. Remember, the physical part is bumpy and flawed. A true geometric counterpart is what establishes the datum. When you reference a flat surface on a drawing as datum A, the actual datum A is the mathematically perfect plane of the granite table you sit the part on, or the perfectly straight axis of the chuck holding a cylindrical part. We measure from the perfect counterpart, not the imperfect physical surface. Section 5, Feature Control Frames. So how do we read all this? Think of it like translating a foreign language, reading strictly from left to right. First, you have the geometric characteristic symbol. Are we controlling position, flatness, profile, runout? Next comes the tolerance value itself, defining the size and shape of our acceptable tolerance zone. This is often bundled with material condition modifiers, like the M in a circle for maximum material condition. Finally, on the right, we list the datum feature references in their strict order of precedence: primary, secondary, tertiary, telling us exactly how to lock the part down before we check that tolerance. Now, as designs get more complex, a single line of control just isn't going to cut it. Notice the difference here between a standard, basic frame and a composite frame. A composite feature control frame stacks multiple geometric requirements one above the other, sharing a single geometric symbol on the far left side. We typically use this for positional or profile controls of a whole pattern of features, like a bolt hole circle, where you need a loose tolerance for the whole pattern's location, but a very tight tolerance between the holes themselves. Understanding how these layers interact is absolutely crucial. In a composite frame, the top layer is called the PLTZF, or the Pattern Locating Tolerance Zone Framework. Try saying that 5 times fast. This upper segment acts as your macro control. It relates the entire pattern of holes back to the main datums of the part. Because it's just locating the whole pattern generally on the part, it typically has a much larger, more forgiving positional tolerance. Conversely, the lower segments of the composite frame form the FRTZF, or Feature Relating Tolerance Zone Framework. These are your microcontrols. They essentially ignore exactly where the pattern is on the larger part, and instead, they rigidly tighten the orientation and location between the features themselves. If you have 4 holes that need to perfectly align with a mating plate, those 4 holes need to have a really tight relationship to one another, even if the entire cluster of holes shifts slightly on the main part. The FRTZF handles that tight internal relationship flawlessly. Which brings us to the very edge of standard tolerancing. We've seen how rule number 1 gives us perfect form envelopes and how composite frames tightly lock down complex patterns. But what happens when the design intent requires us to decouple size entirely from form? How do we handle dynamic profile controls acting on complex surfaces of revolution, where the tolerance zone itself needs to scale and adapt dynamically? That pushes us into the deepest, most advanced chapters of the standard, and it's exactly what we'll be tackling in our next explainer. Keep analyzing those blueprints, and I'll see you next time.
Just picture this total nightmare scenario on the shop floor. You've got a part with a threaded hole. Your coordinate measuring machine, your CMM, runs its probes over the threads and spits out this beautiful, flawless row of green check marks. I mean, the hole measures perfectly in position right at the surface of the part. It is legally 100% in tolerance. But then assembly rolls around, right? And the bolt you thread into it just completely crashes into the clearance hole of the mating plate stacked on top. It passed inspection, but completely failed assembly. So how is this paradox even possible? Well, the answer actually comes down to understanding which geometric space really predicts whether our bolted assembly is going to line up. Think about it. You've got the surface tolerance, that's the physical depth of the hole buried inside the material. Then you've got the mating height tolerance, which is that functional, empty space floating above the part where the fastener actually lives. The crazy thing is, when we just slap a standard position tolerance on a drawing, we're only controlling that first one. We are strictly limiting our control to the depth of the threaded hole itself, totally ignoring where the bolt is going.
So here's the crucial, kind of mind-bending point. A threaded hole can actually tilt around within its positional limits, technically remaining in tolerance at the surface, while aggressively shifting the tip of the bolt way outward. Think of it like a lever. Because the thread is relatively short, a tiny, almost microscopic angular error inside the hole gets massively magnified over the length of the bolt. At the surface, the axis might be off by, just a fraction of a millimeter. But 3 inches up in the air, oh man, that fastener tip has swung wildly out of position, and it's going to crash right into the wall of your mating clearance hole.
And look, the ASME Y14.5 standard actually calls out this exact interference risk. If you look at section 10.4.1, it explicitly notes that unlike a floating fastener setup, where you're just dealing with 2 empty clearance holes, the orientation of a fixed fastener, like a screw or a stud or a press fit pin, is entirely at the mercy of the hole it's driven into. That's a huge distinction. It means you absolutely cannot treat a threaded stud the same way you treat a simple bolt dropping loosely through 2 empty plates. The hole completely dictates the tilt.
So how do we fix this? Well, here is our exact, bulletproof solution for this trap. Straight out of our GD&T symbols reference document, meet the projected tolerance zone symbol. It's a capital P enclosed in a circle. And honestly, when you drop this little symbol into the feature control frame, it does something geometrically profound. It literally extracts the tolerance zone from inside the part's material boundary and projects it outward, right into the air above the surface, extending through the actual height of the engaging fastener.
You can really see the difference when you map it out. Without the modifier, a standard position tolerance zone is basically just a cylinder trapped inside the chunk of metal. But with that projected modifier applied, that cylindrical tolerance zone suddenly floats up into the functional space above the part.
By using this, we are essentially telling manufacturing and inspection, hey, I don't actually care where the hole is inside the block. I only care where the fastener ends up in the air. We completely shift our control to the functional space where the mating part will actually sit.
And guys, this isn't just some optional best practice. It is practically a mandate from the standard for these kinds of applications. The standard clearly tells us that the location and orientation of the threaded hole only matter insofar as they affect the extended portion of that fastener. That's it. Controlling anything else is honestly just wasted manufacturing cost, or worse, giving yourself a totally false sense of security.
Okay, so let's see how this actually builds into a real drawing specification. Step 1, you just place that circled P symbol in the feature control frame, right after your positional tolerance and any material condition modifiers. Simple enough. Step 2, you have to specify the minimum projection height. You write this as a basic dimension right next to the symbol, and it represents the maximum permissible thickness of your mating part. Finally, step 3, you verify this on the shop floor. Now, ideally, this is done using a physical functional gauge with a pin manufactured to that exact projected height. Or you can use advanced CMM software simulation that mathematically extrudes the measured holes axis upward.
Now, there's a really subtle but absolutely vital distinction in the standard when we start talking about studs and pins versus your standard bolts. If you are detailing a drawing with press-fit dowel pins or studs, paragraph 10.4.13 of Y14.5 dictates that your specified projected height has to equal the maximum permissible height of the pin after installation. Not just the mating part thickness. You have to account for the entire exposed length of that fixed pin to guarantee it's never going to bind.
All right, quiz time. Let's test our intuition here with a real-world inspection scenario. Imagine we have two perfectly identical threaded holes on a drawing. One has the projected tolerance zone callout with a 50mm projection height. The other one just has your standard run-of-the-mill position tolerance. Both are going into a thick plate stack-up. Which one actually guarantees your assembly will go together smoothly? Take a second and lock in your answer. Did you guess it? The answer is only the one with the projected zone. Literally, if you skip the projected tolerance zone on a thick threaded stack, you can sail right through your standard CMM inspection and still completely fail final assembly. It's wild. This failure mode pops up exactly when the mating part's clearance holes are just too tight to absorb that unmonitored thread tilt we talked about earlier. By forcing your functional gauges to simulate the pin at its full, real-world projected height, that little circled P guarantees the tilt is caught way before the part ever leaves the machine shop. And hey, if you need the cold, hard mathematical proof, ASME Y14.5 lays it all out right in non-mandatory Appendix B. The standard fixed fastener clearance hole formula is actually pretty straightforward. But, and this is a massive but, the standard explicitly states that this simple formula completely fails to give you enough clearance if your threaded holes are out of square. If you don't use a projected zone, you are forced to use the nightmare tilting axis formula. And trust me, that requires factoring in depth of engagement, maximum projection, and enough trigonometric headaches to make you rethink your career choices just to size a simple clearance hole. Using the projected zone symbol just keeps your math simple, and more importantly, it keeps your assembly safe. Okay, let's tie this all explicitly back to what we covered in our intermediate lessons. Let's look at how this changes what worst case actually means in our designs. You probably recall our definition for virtual condition from Section 3, right? It's that constant boundary generated by the collective effects of a feature's maximum material condition and its geometric tolerance. Basically, it's the absolute worst-case envelope that feature will ever consume.
But here, my friends, is the trap. When you add a projected tolerance zone into the mix, you completely transform that virtual condition boundary. Instead of a boundary buried safely inside the metal of the threaded hole, our worst-case boundary now leaps upward. It turns into this tall, invisible cylinder extending entirely outside the part, representing the absolute extreme tilted envelope of the installed bolt. It's a total paradigm shift.
Think about what this means for you. If you're an engineer designing a stacked assembly, and you try to calculate your virtual condition using just the standard formula, maximum material condition minus position tolerance, without accounting for that projection height, your math is going to be dangerously wrong right at the mating plane. The projected zone is what ensures your virtual condition calculation actually reflects the real physics of the fastener hanging out there in space rather than just the empty hole sitting in the block.
So we know exactly why we need it, and we know how it saves our assemblies from catastrophic interference. But this actually leaves us with a massive, highly advanced question. If this tolerance zone is literally floating in empty air, How in the world does the CMM software algorithm calculate this imaginary projected cylinder based on just the tiny few threads it can actually touch? Well, that mathematical mystery is exactly what we are going to crack in our next lesson. But until then, I want to leave you with this final thought. The next time you look at a thick plate assembly drawing with a standard threaded hole callout, ask yourself, are you inspecting a part that's actually going to work, or are you just carefully measuring a future failure? Join us in Lesson 5 of this explainer series where we are going to crack open ASME Y14.5.1 and go beneath these drawing symbols to uncover the actual hardcore geometric math that defines these boundaries. See you there.
Look, if you're here for Lesson 5, I already know you've got a rock-solid foundation. You know your way around a blueprint, and you can read and apply GD&T symbols in your sleep. But today? Well, today we're doing something a little bit different. We're actually peeling back those graphical symbols you see on the print to reveal the rigorous, completely invisible mathematical layer that literally powers modern automated inspection. You've learned how to read a position tolerance symbol, right? Or a flatness callout. But here is the multi-million-dollar manufacturing question. When a coordinate measuring machine, a CMM, scans a physical part, it just collects a raw, floating cloud of thousands of X, Y, and Z coordinates. So how does the CMM software actually know, mathematically, whether that scattered cloud of measured points passes or fails your tolerance? It doesn't look at a picture on a drawing. It calculates. Okay, let's dive into this. Take a plain language definition of cylindricity. All points of the surface are equidistant from a common axis, right? We all understand that conceptually. But conceptually just isn't enough for a machine. A CMM requires a minimum zone solution. It has to mathematically constrain a massive set of points between exact calculated boundaries. It's the exact same rule, but only one of these definitions can actually be coded into an algorithm.
Which brings us to the foundation of it all, ASME Y14.5.1. If you look right at the very beginning of the ASME Y14.5-2018 standard, specifically in Section 1.1, it explicitly tells us, for a mathematical explanation of many of the principles in this standard, see ASME Y14.5.1m. It's right there in the scope. Y14.5.1 is essentially the mathematical rulebook. It exists for one reason, to provide precise, totally unambiguous mathematical definitions for the exact same tolerance concepts we describe graphically in Y14.5. And guys, this is the absolute bedrock that CMM software, GD&T-aware CAD tools, and tolerance analysis software actually run on. And this brilliantly illustrates the divide. Think about standard GD&T symbols for a second. Flatness, position, profile. We type these out, we place them on drawings, we read them. Symbols are an incredibly efficient language for us humans, but CAD tools and CMMs, they cannot run on graphical fonts and keyboard alt codes. A computer needs an equation and literally needs to know how to establish a true geometric counterpart using pure math.
So let's talk about the mechanics of how it does that, starting with the minimum zone concept. When a CMM probe touches a part's surface, it gathers thousands of spatial data points. Now, the Y14.5 standard requires us to check these points against specific boundaries. To pull this off, the CMM software algorithm seeks the best fit mathematically. So for example, if it's checking flatness, the software isn't just looking at the points. No, it's actively trying to find two perfectly parallel planes that enclose every single measured point, and then it calculates how close together it can squeeze those two planes. That tightest possible boundary? That's what we call the minimum zone.
I want you to try a quick mental exercise with me. Imagine a 3D space filled with this scattered cloud of points from a rough machine's surface. If I handed you two perfectly flat, invisible panes of glass, how exactly would you angle and position them to trap all those points in the absolute thinnest space possible? It's kind of like a giant puzzle, and it's incredibly difficult for a human to estimate visually. But this is exactly what the software does, thousands of times a second. Here's how that process actually flows in the system. First up, the CMM registers that scattered spatial data. Next, the software applies the outer theoretical bounds based on your specific GD&T callout. And finally, the algorithm goes to work. It actively iterates, converging those theoretical boundary planes, or cylinders, depending on the callout, twisting and shifting them mathematically until it finds the absolute tightest fit. The final distance between those converged boundaries, that is the actual deviation the CMM reports back to you. Now, this brings up a huge real-world issue, why two CMMs can actually disagree. So, the crucial point here is, this is exactly why two different CMMs, or even two different software packages, might give you slightly different numbers for the exact same physical part.
You'll often hear people dismiss CMMs as unreliable or glitchy when this happens, but really, that's just a misunderstanding of the math. Let's look at what's actually going on under the hood.
Now, what's really interesting about this slide is what happens when we compare physical reality with digital computation. As the Y14.5 standard points out, manual inspection relies on physical datum feature simulators, stuff like a chuck, a vise, or a gauge block. And those physical items have inherent manufacturing errors of their own. But CMM software, it builds a true geometric counterpart, which is, by definition, mathematically perfect. On top of that, remember that algorithmic iteration I just mentioned? Well, different software companies might use slightly different mathematical approaches to converge on that minimum zone. Understanding this math helps us explain rather than just wave away those minor discrepancies you might see on an inspection report.
Let's look at another specific application of this: axis versus surface computations.
For example, let's look at a scenario where a geometric tolerance is applied with a zero tolerance at maximum material condition, or MMC. The standard dictates two very distinct computation methods here. In the surface method, the software checks that the feature surface does not violate a virtual condition boundary that's equal to the MMC size. But if the software is utilizing the axis method, it has to apply completely different mathematical constraints. It has to verify that the feature's actual unrelated axis or center plane doesn't violate a dynamically sousing tolerance zone. The software absolutely has to know which mathematical constraint to apply because checking a surface boundary versus checking an axis line require fundamentally different lines of code.
So we've just uncovered the intense algorithmic complexity required to evaluate a single feature against a mathematically perfect true geometric counterpart. It's a lot, right? Well, here's a thought to leave you with. If the minimum zone iterations and boundary checks are this incredibly rigorous for just one simple hole or flat surface, how on earth does the software calculate the math for complex, repetitive feature patterns that are tied to multiple pattern datums? No way it's simple, right?
Let's move on and see how this builds into our next topic. We'll see exactly how software untangles that crazy web in Lesson 6, where we return to practical, high-complexity print scenarios to see how these mathematical rules scale up. Thanks so much for joining me on this explainer, and I will catch you in the next lesson.
Welcome back to our Advanced GD&T Masterclass Explainer. Today, we're diving straight into what I honestly consider the ultimate engineering puzzle, and that is untangling competing feature patterns on a single complex part. Now, since you're already solid on single pattern as datum concepts from the intermediate tier, you're in the exact right place. We're jumping up a weight class today, looking at parts with multiple, sometimes nested patterns that are literally fighting to be the boss of your design.
All right, let's kick things off with a little mental exercise. Picture this. You've got a large flange. It's got two separate bolt hole patterns, an inner ring and an outer ring. Both are potentially usable as datums, and both are absolutely, undeniably critical to the part's function. But before we crack open the standard, I want you to commit to an answer in your head. If I tell you that the inner ring mates with a high-precision shaft coupling and the outer ring just mounts to a static wall, which one dictates the geometry? Which pattern actually gets to be the reference, and what happens to the other one? Seriously, lock in your answer right now. Got it? Good, because here's the wild part. Making that choice isn't just about swapping a letter on a drawing. If you declare datum B as the inner bolt hole pattern versus the outer pattern, you are quite literally producing two completely different populations of acceptable parts from the exact same nominal design. Guess wrong? Or just pick what's easiest to measure on the CMM, and it's a massively costly mistake. So which one did the designer actually intend?
To solve that, we have to go straight to the source. The ASME Y14.5 standard, specifically section 7.8, gives us our golden rule. It says, a datum feature is selected on the basis of its functional relationship to the toleranced feature and the requirements of the design. Basically, design intent is everything. Which pattern is functionally more critical? Your datum selection absolutely must be driven by how these parts physically mate in the real world. It's not about what makes the quality inspector's life easier.
So applying that golden rule back to our flange, the answer is pretty clear, right? Because our inner ring mates with that precision-located shaft coupling, it acts as the functional anchor, so it should absolutely become your primary pattern datum. Now, the standard does throw in a few practical caveats. The datum feature obviously has to be accessible, and it needs to be of sufficient size to actually be usable. But since our inner ring handles that high-precision mating component, it checks the functional box perfectly.
Moving right along into Section 1. Composite tolerancing for nested patterns. We'll be looking at applying PLTZF and FRTZF.
Okay, so once we've locked in that inner ring as our functional datum, the next big hurdle is figuring out how to apply tolerances to the outer ring so it relates correctly to both the inner ring and to itself. This is exactly where nested composite tolerancing comes in. Under Section 10.5.1, the uppermost segment of a composite feature control frame is your PLTZF. Think of this as the big picture locator. It defines the larger tolerance zone that locates the pattern as an entire group, locking it in relative to your reference datums.
Then you've got the lower segment, the FRTZF, your feature relating control. This guy is the micromanager. It governs the tighter, smaller positional tolerance for how each individual hole relates to the other holes within that exact same pattern. The real beauty of this setup is that while the FRTZF keeps the hole-to-hole spacing super tight, the entire pattern as a group is totally free to translate or rotate within the larger bound set by the PLTZF above it.
Up next, Section 2, Finding the Pattern Center, where we tackle nominal versus actual center challenges.
Look, drawing perfect circles in CAD is a breeze, right? But out in the real world, how do our inspection tools actually figure out where the center of a multi-feature pattern is when the physical holes are imperfect? Well, the standard defines what's called a datum feature simulator. Since datums are theoretically perfect, we need a physical stand-in for that perfection, like a flawless set of gauge pins on a fixture block. Those pins act as the simulator to engage our imperfect datum holes, which locks down the rotational constraint and establishes our true center axis.
But wait, this is where things get genuinely wild. What happens when we throw maximum material condition, or MMC, into the mix for our datum pattern? If we specify MMC, our simulator pins are fixed at the virtual condition, basically the smallest allowable holes. If the machinist drills those holes even a little bit larger than the smallest limit, they gain what we call bonus tolerance. The physical holes are now larger than the perfect simulator pins, meaning the part can legally shift or wiggle around on the fixture. So that best fit center of your part, it just became highly dynamic.
And if you get this next concept backward, oh man, you are setting yourself up for a world of pain. You can easily pass 100% of your parts in the quality lab. The CMM glows green, all the tolerance zones check out perfectly, but when those parts actually hit the factory floor, they are completely impossible to assemble. So why exactly does this happen?
That brings us to Section 3, Simultaneous versus Separate Requirements, which is all about coordinating interacting patterns.
Here's the root of that assembly nightmare. It all comes down to how the ASME standard treats multiple patterns by default. If your inner bolt ring and your outer bolt ring reference the exact same datums in the exact same order of precedence, the standard automatically clumps them together into a simultaneous requirement. That means the inner and outer patterns are treated as one single, locked together super pattern. Their tolerance zones cannot translate or rotate independently. But wait, what if your inner ring mates to one component on a Tuesday and your outer ring mates to a completely different component on a Thursday?
If they mate to different components at completely different stages of assembly, artificially locking them together on the drawing is going to cause major assembly failures. And that is exactly why you have to explicitly add the SEP-RET, or Separate Requirements note, right next to your feature control frame. Slipping that note in allows those two patterns to establish completely separate datum reference frames. They can now shift and rotate totally independent of one another to take advantage of that bonus tolerance we talked about. This is literally the exact tool you need for parts that assemble in stages. Boom! Flange mystery solved. We now know how to select the true functional datum, properly apply composite tolerances, and use that all-important SEP-REQ note to make sure everything actually goes together on the assembly floor. But of course, solving one problem just reveals a bigger one for our next explainer. We've mastered these complex prismatic patterns, but how on earth do we apply these rules to completely organic, non-prismatic geometry that literally has zero straight edges? Join me next time for Lesson 7, where we tackle advanced profile tolerancing for freeform and 5-axis machine surfaces. You won't want to miss it. Video title: Master GD&T Complex Pattern Datums. 3 thumbnail concepts. 1. The choice. A split screen showing a blueprint of a flange. On the left, the inner bolt holes are highlighted in red. On the right, the outer bolt holes are highlighted in red. Big, bold text overlays the center, which is the datum. 2. The shift. An exaggerated visual of tolerance zones, glowing blue cylinders, visibly shifting out of alignment from a set of bolt holes. Text overlay: stop passing bad parts. 3. The secret code. A zoomed-in macro shot of an ASME feature control frame, with the text SEP-RET highlighted in bright, glowing yellow marker. Text overlay: the one note you're missing.
If you've been following along, you already know the fundamentals of surface profile and unequal zones. But now, we're taking those concepts and applying them at absolute production scale to the most complex shapes imaginable.
Think about the complex geometry of a modern turbine blade, or maybe a sweeping mold tool surface. We are literally talking about thousands of individual points that all need to be controlled. You can't exactly just slap a simple flatness or position symbol on an organic shape like that, right? I mean, there's no single flat plane or simple cylinder to reference. So how on earth does an entire complex 3D shape get locked down with just one requirement? Well, we're going to see exactly how Profile scales up to handle this level of complexity.
Check this out. It's a bit of a pattern interrupt. On one side, we've got a traditional, simple, flat part profile callout. It just controls a few distinct reference points. But on the other side, we have a full freeform surface with a profile tolerance wrapping the entire model. And here is the kicker. It is the exact same symbol on the drawing. No way, right? But the freeform application is controlling orders of magnitude more geometry at once. So what actually changed here? How does the math stretch to cover the whole part?
Let's dive straight into Section 1, the True Profile and NBD.
The ASME standard spells it out pretty clearly right here, and this concept is really the foundation of it all. Profile is the absolute tool of choice for organic surfaces because it directly references the mathematically defined true surface right from the 3D model itself. We call this model-based definition, or MBD. Unlike simplified planar logic where you project a 2D line, the profile tolerance zone establishes a 3D boundary that completely follows the exact digital contours of your CAD model. It honestly doesn't matter how much the cross-section varies or tapers. The tolerance zone perfectly offsets from that digital data file.
Now, what's really fascinating here is the dynamic profile modifier. When this was introduced in the 2018 standard, it was a total game changer for complex surfaces. Usually, a profile tolerance zone is static. It controls both the form and the overall size of your feature. But what if you just need to tightly control the aerodynamic form of a shape without rigidly locking down its overall size boundary? That is exactly what this modifier lets you do. It lets the form be controlled completely independent of size.
Looking at our symbol chart, you'll see the dynamic profile symbol is represented by that little triangle inside the feature control frame. Adding this symbol is huge. It means your 5-axis mill can hit that complex organic shape perfectly, maintaining the exact required aerodynamic curvature, without the part getting scrapped just because the entire blade ended up uniformly a few thousandths of an inch thicker than nominal. It completely separates the requirement for shape from the requirement for size.
Moving right along to Section 2, Composite Profile at Scale.
Okay, quick pop quiz for you. Imagine you're tolerancing a turbine blade. Which of these two strategies better reflects real aerodynamic priorities and actually keeps your manufacturing costs in check? Option A applies a blanket uniform profile tolerance across the entire freeform surface, or Option B uses a composite profile to put a really tight tolerance on the critical leading edge while leaving a much looser tolerance on the trailing region.
If you guessed Option B, you hit the nail on the head. It wins every single time. Honestly, applying a uniform, microscopic tolerance across an entire massive surface is just a great way to bankrupt a manufacturing project. Instead, we use the composite profile framework. We combine a looser overall form and location control for the general surface with tighter, localized zones in functionally critical regions like sealing surfaces or leading edges.
And this brilliantly illustrates how the standard handles that composite logic. Just like we learned with position tolerances, a composite profile feature control frame has multiple segments. The upper segment, that's your profile locating control. It locates the massive surface to your datums, constraining both translation and rotation. Then you have the lower segment, which is the profile feature control. That one strictly dictates the tighter form and orientation of the feature, and it's constrained only in rotation relative to those datums. The actual physical surface has to live inside both of these zones simultaneously.
Which brings us to Section 3, verifying millions of points.
So, how do you actually check this on the shop floor? The 5-axis verification challenge means moving completely away from traditional metrology. You can't just touch a few random points with a hard probe and call it a day. Instead, you're using a CMM or a laser scanner to generate a massively dense point cloud of the physical part. Then, specialized software overlays those tens of thousands of scanned points directly against the CAD model's mathematically defined true profile.
What you get back is this incredible visual deviation map. Imagine a 3D model just glowing in greens, yellows, and reds. The hotspots on that map instantly reveal exactly where the tool deflected or where the material warped during the machining process. It makes it instantly visible if that tight lower segment requirement we just talked about was violated by a local high spot. You are literally inspecting a continuous surface with continuous data.
All right, let's talk real-world impact in Section 4, the cost of precision.
I really want you to focus on this one word right here. Hours. Literally, hours. One tiny small change to tighten a composite profile's lower segment tolerance can shift a 5-axis machining cycle time by hours per part. Think about it. To hit tighter freeform profiles, a CNC machine has to take way smaller stepovers, drastically slow down its feed rates to avoid tool deflection, and use much more expensive tooling.
You absolutely must aggressively balance your tolerance tightness against inspection and machining costs. Freeform tolerances scale cost non-linearly compared to simple prismatic features. Making a flat block twice as flat, that might cost you 10% more. Making a complex turbine blade twice as accurate, that might cost 500% more. That is exactly why you only use tight composite zones where they are absolutely functionally critical, and why you should leverage that dynamic profile modifier whenever you care more about the aerodynamic shape than the overall size.
So, I want to leave you with a provocative thought to wrap up this explainer. If we now know how to elegantly control a massive, complex, continuous surface carved from a single block of titanium, how do we extend these exact same profile and datum concepts across parts that are completely separate, joined, and welded together? Well, that is exactly what we are going to unpack in our next lesson when we tackle GD&T for weldments and multi-body assemblies. You definitely won't want to miss it.
Let's jump right into this explainer, because we are tackling one of the absolute most frustrating realities in manufacturing. You know the drill. You design this large, beautiful, perfectly flat structural assembly in your CAD software. Every dimension is crisp. Every surface is literally flawless. But out on the shop floor, well, you have to ask yourself an incredibly difficult question. How do you tolerate something whose final shape is practically determined by the chaotic heat of a welding process rather than a precise CNC machine? Picture a massive fabricated weldment. You start with perfectly flat steel plates tacked together exactly to your specifications. But the exact moment you apply the intense, concentrated heat required to actually weld those plates together, the metal undergoes massive thermal expansion and contraction. And that creates a serious challenge for anyone used to machining solid, rigid blocks. Think about it. Before welding, those individual flat plates are perfect. But the final welded assembly, it's visibly warped and distorted from all that thermal energy. The print calls out tolerances on the final welded assembly, so we have to figure out which state actually matters. And more importantly, how do we measure this distorted shape fairly without scrapping parts that would absolutely perform perfectly in the field?
Let's look at Section 1, the blueprint, focusing on a two-stage tolerancing strategy.
To solve this, the heavy equipment and structural fabrication industries rely on a very specific approach. They don't just throw a single set of tight tolerances on the final print, cross their fingers, and hope the welders can work miracles. No way. Instead, we use a two-stage strategy. Step 1 is component tolerancing. This means specifying tolerances on the individual plates before welding to guarantee a good fit-up. Because think about it, if your pre-weld components don't fit together tightly, your welders have to fill massive gaps. That means applying even more heat, which equals even more distortion. Then step 2 is assembly tolerancing. Once the heat has done its thing and warps the structure, we use a completely separate set of tolerances on the final assembly to control how it actually interfaces with other parts. Moving right along to Section 2, datum strategy and controlling the chaos. If you try to take a warped welded box and rest it against a perfectly flat granite surface plate, it's just going to rock back and forth. You have absolutely no stable reference frame. And this is exactly why the datum targets we covered in past lessons become absolutely essential here. Full surface datums completely fail because as-welded surfaces are almost never flat enough to ensure reliable contact. So instead of trying to use an entire wavy, warped face as your foundation, you define specific contact points, lines, or small areas. This lets you create a highly repeatable, rock-solid coordinate system straight out of a bumpy, raw surface. And it's actually wild to see how the standard handles this. ASME Y14.5, Section 7.24 explicitly calls out surfaces of weldments as the textbook example for why you'd need to use datum targets. The standard straight up acknowledges that because of inherent irregularities and induced distortions, you simply cannot use the entire surface effectively. It completely validates why we mathematically avoid the chaotic full surface. All right, Section 3 is post-weld machining, or as I like to call it, where perfection returns. So the real crucial point is figuring out how we bring precision back to a distorted part
You've got this warped assembly, right? But it might have a critical mounting face that needs to bolt totally flush against an engine block or a transmission housing. You obviously can't just leave that mounting face rough and warped. You have to bridge the gap between rough fabrication and precision assembly. So let's test your intuition for a second. It's a print flag some features as machine after weld and others as welded. Which ones are getting the tight GD&T? I mean, imagine a heavy structural rib that just holds the frame together versus that critical mounting face.
Exactly. The machined features carry the tight functional geometry, while the raw weldment retains much looser tolerances. The clever engineering strategy here is to weld the whole structure together first, let it warp, let it cool completely, and then put the entire assembly into a CNC mill. You machine that mounting face perfectly flat and true to your datum targets. This wipes out the weld distortion exactly where it matters most, while leaving the rest of the structure alone.
This brings us to Section 4, the reality check, and what we call the restrained condition trap.
Now, we are talking about the absolute biggest mistake inspectors make on the shop floor, a trap that costs manufacturing companies massive amounts of time and money every single year. If you measure a flexible weldment freestanding, you can easily reject a perfectly good part. When a massive welded frame is just sitting loose on an inspection table, gravity and its own internal thermal stresses might cause it to twist slightly. If you measure it right then, it might look like it's completely out of tolerance. But in the real world, this part is going to be bolted down tightly using heavy hardware, right? As you might remember from our intermediate lesson 10 on flexible parts, the free state assumes no external forces other than gravity. That's perfectly fine for rigid, solid steel cubes. But measuring a massive, slightly flexible weldment in its free state gives you a completely false representation of how it's actually going to act in the real world. ASME Section 7.20 confirms that parts can, and often should, be measured in a restrained condition, meaning we use physical force in a fixture to simulate the final assembled state. The standard explicitly states that to make the part comply with the datum feature simulators, forces may be applied to flex or deform the part. Guys, this is huge. It means you are legally allowed, per the standard, to clamp the part down during inspection, mimicking exactly how it will be bolted down in the field. Picture your weldment clamped into its checking fixture. The rough points hit the datum targets, it flexes into its functional shape, and suddenly, it passes inspection. The clamps simulate the installation bolts. The twist from the welding heat is just pulled right out by the physical restraint, and you can measure that finished machine mounting face perfectly relative to your datum targets. This is literally how you stop rejecting perfectly good parts that will work flawlessly once they're bolted into the final product.
Which leads perfectly into Section 5, the economics of GD&T, connecting tolerances to cost.
Every single decision we just discussed, from datum targets to post-weld machining, has a massive financial consequence. Specifying tight tolerances on an as-welded surface that doesn't actually need it, that will skyrocket your scrap rates. On the flip side, intelligently utilizing a two-stage tolerance strategy, datum targets, and restrained condition measurement keeps your manufacturing costs grounded while completely guaranteeing your assembly will fit together. Think about it. If you don't understand the exact cost of the tolerance you just specified, can you really afford to put it on the drawing? We're going to unpack all of that in Lesson 9, exploring design for manufacturability. But until then, ask yourself this. How many perfectly good, functional parts is your shop floor throwing in the scrap bin right now simply because they're measuring them wrong? I'll see you in the next one. By now, you know the symbols. You know position from profile. But today is all about judgment. It's about choosing the right tolerance, not just the mathematically correct symbol, because your choices literally dictate the financial reality of the entire project.
Just think about these two identical part designs for a second. We've got one with a standard tolerance callout, costing $12 a unit to manufacture. Then we have the exact same physical design, but with a slightly tightened dimensional tolerance. That one simple change, just moving a decimal point, turns a $12 part into a $340 mistake. It's the exact same geometry. The only difference is the tolerancing choice. See, very often an engineer will tighten a callout, just to be safe. They want to ensure everything assembles perfectly, so they just squeeze that tolerance zone down. But they do this without ever actually checking the statistical process control data of the machines cutting the metal. When you tighten a callout just to be safe, without looking at the real capability of the manufacturing process, you really have to ask yourself, who pays for that mistake? Well, the answer is your project budget and ultimately your company's bottom line. Okay, Section 1, Statistical Process Control Reality. We really need to bridge the gap between the strict, theoretical geometry of the ASME Y14.5 standard and the cold, hard financial reality of the shop floor. A lot of people think GD&T is just about rigid boundaries, but the standard actually explicitly provides for statistical tolerancing in Section 3.60. It defines it as assigning tolerances to related components on the basis of sound statistics. So this is the missing link, right? The link between what tolerance would be nice to have and what is actually achievable at a reasonable cost. We have to assign limits based on process capability metrics like CP and CPK, not just guessing what looks safe on a drawing.
Let's do a quick quiz to put this into perspective. Say we have a feature, hole A. Your required functional tolerance is plus or minus 0.1, but the process capability data, the CPK from the actual shop floor, indicates the machine's natural limit is plus or minus 0.3. So can this machine reliably hold what you're asking it to do?
The answer is obviously no, because your requirement is exactly 3 times tighter than the natural capability of that manufacturing process. You are literally demanding a level of precision that the machine physically cannot produce consistently without massive intervention, endless tweaking, and just terrifyingly high scrap rates.
Which brings us to Section 2, the nonlinear cost curve.
This concept brilliantly illustrates what happens when you push a machine past its natural capability limits. It doesn't just get a little more difficult. The economics completely break down. Notice how the cost of manufacturing doesn't just increase proportionally as tolerances tighten, it explodes exponentially once you hit that danger zone near the machine's natural capability limit. Moving from a standard tolerance to a tight tolerance, okay, that might double your cost. But moving from a tight tolerance to a very tight one, pushing past what the machine can naturally do, costs just rocket upward. You're suddenly paying for custom tooling, constant operator intervention, slower feed rates, and basically throwing away half the parts you make.
So the practical rule here, and the absolute crucial point, is functional tolerancing. We talked about this way back in the beginner stages of this masterclass, but it really bears repeating now with this new financial context. You should only tolerance as tight as the function actually requires. Literally every single tighter than needed callout adds pure exponential cost with absolutely zero functional benefit to the final assembly. It is just wasted money.
All right, moving into Section 3, strategic bonus tolerance levers. Now let's turn all this into actionable solutions, because you might be sitting there thinking, but I need my parts to assemble. And you do. But ASME Y14.5 gives us some absolutely brilliant tools to loosen individual tolerances without ruining the assembly function. These are our legitimate levers for generating bonus tolerance and dramatically lowering costs. Maximum material condition, least material condition, composite positional tolerancing, and the statistical root sum square stackup. Instead of just defaulting to a rigid, regardless of feature size requirement, top engineers use these levers to give the shop floor maximum breathing room. Let's look really closely at Section 5.9.4, covering the effect of MMC. By applying a maximum material condition modifier, that little M in the circle, the standard intentionally gives you additional allowable variation as the feature departs from its maximum material limit. So if your hole is drilled larger than its smallest allowable size, but still within size limits, you get bonus positional tolerance. It's amazing. You are basically giving the machinist free leeway precisely when the assembly conditions allow for it.
And the exact same cost-saving logic applies to LMC under Section 5.9.6. It grants additional geometric tolerance as a feature departs from the least material condition. This is incredibly useful for things like preserving wall thickness on castings. It keeps the part completely functional while minimizing scrapped parts, which directly pulls you out of that exponential cost danger zone we saw earlier.
Section 4, Case Study, 3 Callouts. Let's see how one feature can be toleranced 3 different ways and the massive impact that has on your budget. Compare these 3 identical features. First, the tight regardless of feature size callout. There is no bonus tolerance allowed here. It's incredibly expensive, and honestly, it's a completely poor match for natural process capability. Next, we use MMC. Now we have bonus tolerance. The cost tops to a manageable medium, and it forms a genuinely good capability match. Finally, we use a composite tolerance. Here, we get bonus tolerance for location and pattern orientation. The cost literally plummets to the lowest possible level, and it perfectly matches the natural capability of the CNC machine.
Let's break down why that third option is so incredibly powerful. A Section 10.5.1 details composite tolerancing is a brilliant lever. It lets you create a pattern locating tolerance zone framework, which gives a larger, much cheaper tolerance for where the overall pattern sits on the part.
Then, you use the feature relating tolerance zone framework to keep a tighter tolerance only within the pattern, feature to feature, meaning you only pay for high precision exactly where the mating part actually requires it. And hey, if you are taking full advantage of statistical process controls, you can move away from those worst-case arithmetic stack-ups. You can use the RSS formula, the square root of the sum of the squares, to mathematically prove that individual assembly tolerances can be safely loosened. Why? Because the statistical probability of every single part in an assembly being at its absolute worst-case limit simultaneously is incredibly low. So you can widen the individual drawing tolerances and still guarantee assembly.
Okay, Section 5, the Design Review Lifesaver. We are entering the phase of this explainer that has literally saved real production programs 6 figures in manufacturing costs. If you take one single practical habit away from this session, please let it be this next question. You must rigorously ask this single design review question of every single blueprint, of every single feature control frame. Does this actually need to be this tight? Seriously. Do not accept we always do it this way or it's just a standard block tolerance. Force your team to justify the tolerance against the functional requirement and the shop floor's actual process capability.
But just remember the standard's direct caution. If you do use the statistical tolerancing symbol, the ST modifier, to widen those limits on the drawing, you must clearly specify the necessary statistical indices. The drawing has to mandate that the features be produced with statistical process controls, so the shop knows they actually have to monitor their CPK to maintain that wider tolerance safely.
So to wrap up our framework for today, avoid the incredibly expensive mistake of over-tolerancing. Remember that cost increases exponentially, not linearly. Match your functional limits to real process capabilities. And for the love of your budget, use the standard's built-in bonus modifiers like MMC, LMC, and composite symbols to buy yourself some breathing room without sacrificing the assembly. At the end of the day, this kind of judgment is exactly what separates a CAD drafter from a master engineer.
Now that you know how to balance geometry with cost, and you have your perfectly optimized, financially sound drawing, we have to ask a slightly terrifying question. What happens when these prints leave your desk and turn into legally binding manufacturing documents? Because out in the real world, a misunderstood symbol isn't just a mistake, it is a breach of contract.
And that is exactly what we will uncover in Lesson 10. We'll be exploring the legal and contractual role of the engineering drawing and seeing how ASME Y14.5 holds up when the lawyers get involved. Until then, ask yourself, how much money is currently hiding inside your company's standard tolerances? Think about it, and make sure you join me for that critical next explainer.
Video title, The $340 Mistake, GD&T Tolerancing for Cost. One-line YouTube description. Learn the exact framework top engineers use to balance GD&T precision with manufacturing cost and process capability. Thumbnail concepts. 1. The split screen hook. A split screen showing a simple CAD part blueprint. Left side, $12 with a standard tolerance. Right side, $340 with a slightly tighter tolerance. A giant red arrow points at the tight decimal. 2. The over-tolerance stamp. A stressed manufacturing engineer holding a machined part with a giant glowing red stamp over the blueprint that reads over-toleranced. 3. The danger zone curve. A line graph showing a rocket ship trajectory of cost as the x-axis, tolerance, shrinks, with a warning sign reading danger zone near the natural capability limit.
So if you've been following along with our masterclass, you are already totally fluent in reading and writing GD&T. But today, we're kind of shifting gears. We're going to stop looking at engineering prints as just technical diagrams and start looking at them for what they really are, legally binding business documents. This lesson is all about what that finished print actually means the moment money changes hands.
Okay, let's kick this off with a scenario. Imagine a supplier delivers a massive batch of parts. Your inspector checks them, and wow, every single dimension is absolutely perfect. But when they hit the assembly line, they completely fail. The parts just do not work as intended. Naturally, the customer rejects them, but the supplier is demanding payment because, well, they hit the numbers. So who's actually right here?
Let's get right into Section 1, the $1 million dispute.
What exact document actually settles an argument like that? Well, the crucial point to understand is that meets print is almost always the standard both parties are held to. When an engineering drawing or an MBD model is referenced in a purchase order or a supplier contract, it's no longer just a suggestion. It literally becomes the technical specification of what is legally owed. That means the precision in every single G&DT symbol we've covered so far has real, tangible financial consequences. Basically, if the print was perfectly met, the supplier generally gets paid. And yeah, that's true even if the engineer completely failed to tolerance the functional requirements properly.
Moving on to Section 2, the title block contract.
Let's actually step away from those complex feature control frames for just a second and look at a pretty unglamorous corner of the drawing. See, calling out the specific ASME Y14.5 standard right down in the title block is exactly what gives all your GD&T symbols their actual power. You can draw all the profile and position symbols you want all over a part, but without a foundational standard dictating their exact mathematical interpretation, they're really just pretty pictures on a page.
In fact, the ASME standard explicitly requires this notation right in Section 1.3. And why does this matter so much? Well, without it, the drawing might be interpreted under a completely different default standard, maybe an older edition like 1994 instead of 2018, or maybe even an entirely different international standard altogether. And as you know, a single symbol can mean two slightly different things across those standards, which completely changes the contractual obligations of the manufacturer.
Which brings us to Section 3, ambiguity equals business risk. The danger here is just massive. When you apply a direct tolerance without clear origins, you create this huge chasm between what the engineer assumed in their head and what the machinist actually measured out on the floor. An engineer might look at two surfaces, apply a simple plus or minus location dimension between them, and just assume everyone knows how to measure it. But, as we know from our advanced studies, parts are literally never perfectly flat or perfectly straight in reality.
And ASME Section I 2.2 is super clear on this. When you just throw a dimension between two surfaces, there is no defined measurement vector. So the supplier measures left to right, it passes. The customer measures right to left, it fails. And the crazy part is, both are technically valid inspection results. This is exactly how you end up with rejected invoices, massive arguments, and completely broken supplier relationships.
Now, before we go any further, I definitely need to state clearly that we are discussing general engineering practice here and how drawings function within the industry. This is not legal advice. Real, actionable disputes over rejected parts always involve contract law, and if you ever find yourself in one of those, you for sure need to involve qualified legal counsel. Our goal in this explainer is simply to keep you out of that lawyer's office in the first place by writing airtight engineering specs.
All right, let's jump into Section 4, the missing datum quiz.
Let's put this into practice and see if you can spot a $1 million mistake. Imagine you're looking at a print, and a critical feature, say a hole that absolutely needs to align with a mating part, has a position tolerance, but it is missing a clear datum reference in its feature control frame. What specific business risk does that ambiguity create during the inspection process? Think about how you would actually go about measuring that part.
Remember, a datum is perfectly theoretical, but a datum feature is the actual, imperfect, physical feature on the part. If you don't explicitly dictate how the part is locked down in space, the supplier gets to choose. Because the physical feature is imperfect, failing to specify it means the inspector has zero instructions on how to set up the part. The physical tooling, the fixture, the surface plate they use, it's all legally up for debate now. And honestly, they're naturally going to choose the setup that passes their parts, regardless of whether it actually functions for your final assembly or not.
Let's look at Section 5, the revision block reality.
This is another highly overlooked area that becomes absolutely critical the exact moment parts get rejected. The revision block isn't just administrative paperwork, it's quite literally a timeline of your contract. You might place a purchase order when the drawing is at Rev A. A couple of weeks later, engineering updates a tolerance and saves Rev B. Then, by the time the parts arrive, your system shows Rev C. If those parts fail, the very first thing pulled in a dispute is the purchase order to ask, wait, which version do we actually agree to? If your procurement system doesn't perfectly lock that purchase order to the specific revision level, you might find yourself holding a supplier accountable to a tolerance they never legally even saw.
And finally, Section 6, preventing future print disputes.
We've seen exactly how ambiguity directly translates to financial liability, so how do we stop these bad prints from ever reaching a supplier in the first place? Well, in Lesson 11, we're going to build a systematic checklist to audit your drawings specifically from a business perspective. We'll learn how to hunt for these legal traps before a single piece of metal is ever cut, because at the end of the day, an engineering print is only as good as the contract it enforces. Let me leave you with this. If your most expensive critical drawing went to court tomorrow, are you absolutely sure you'd win? Think about it. Join me in the next explainer, and let's make sure you do.
Okay, let's dive right into this by picturing a scenario that we've all either seen or completely dreaded. You're sitting in a design review. A massive, complex print, which was already approved by the junior engineering team, is put up on the screen. A senior engineer takes one look at it and within 90 seconds points out a critical tolerancing error that would have scrapped thousands of dollars in parts. How in the world did they do it so fast? Well, welcome to Lesson 11 of our Advanced GD&T Masterclass Explainer. Today, we're taking absolutely everything you've learned so far and consolidating it into a highly practical, repeatable review process.
I want you to try scanning a busy, complex engineering drawing right now and spot an error in 5 seconds. Seriously, try to find a missing basic dimension, maybe a conflicting tolerance, or a totally bad datum callout just by looking at it. You'll quickly realize that random scanning simply doesn't work. Your eyes dart everywhere, you get completely overwhelmed by the sheer density of numbers and symbols, and critical errors just slip right past you.
The secret here is that master engineers aren't randomly scanning the page. When that senior engineer caught the error in 90 seconds, they weren't just passively staring. They were aggressively running through a highly structured mental checklist. They know exactly what they are scanning for, and more importantly, in what exact order. And that is exactly the system we are going to build together right now. So here is that 6-step systematic GD&T audit checklist. Title block and standards, datums, FCFs, SIM and SEP requirements, cost check, and consistency. It is specifically designed to take you from guessing to catching errors with absolute certainty.
Let's kick things off with Step 1, checking the title block for the correct standard and edition.
Before you look at a single tolerance, you absolutely must establish the rules of the game. Imagine a print doesn't specify the exact standard, like it doesn't explicitly call out ASME Y14.5 2018 versus the older 2009 revision. The entire interpretation of the limits of size can be compromised right out of the gate. The standard establishes your fundamental rules, your tolerancing defaults, and how dimensions actually relate to the 3D model or 2D drawing. If that foundation is ambiguous, literally every symbol on the print becomes legally and functionally debatable.
Moving right along to Step 2, Datum Feature Selection, focusing on functional and logical precedents.
Datums are the anchors of your part, right? So if the anchors are wrong, the entire inspection fails to replicate reality. You have to ask yourself, are the datums actually controlling the critical mating features? Are they placed in a logical order of precedence, primary, secondary, tertiary? And are the datum features themselves fully controlled for form or orientation before they're used to control other features? If you spot a primary datum resting on some rough, untoleranced cast surface, that is an immediate red flag.
All right, Step 3 is where the heavy lifting really happens, checking every single feature control frame for completeness and correct formatting. Listen, this step alone catches about 80% of real-world print errors. The absolute fastest way to scan a feature control frame is strictly left to right. First, check the geometric characteristic symbol. Second, check the tolerance zone and any material condition modifiers, like maximum material condition. Finally, check the datums to ensure they are in the exact correct order of precedence. It's really that systematic. Let's do a quick pause and spot micro quiz using our 14 symbols reference table. Look at the form category: straightness, flatness, circularity, and cylindricity. Do they require a datum reference? No. Form tolerances never reference a datum because they control a feature relative to itself. So if your left-to-right scan hits a flatness symbol and you suddenly see an A or B in the datum boxes at the end of that frame, boom, it is an indisputable failure. You just caught the error.
A feature control frame is simply a rectangular box combining those geometric symbols, tolerance values, modifiers, and datum references. And this brilliantly illustrates why you have to ensure the tolerance zone shape actually matches the design intent. Say you're controlling a hole with a positional tolerance. Did the designer remember to put the diameter symbol before the tolerance value? If it's missing, the default is a planar tolerance zone, not a cylindrical one. That drastically changes the acceptable deviation. But your left-to-right scan is going to catch this every single time.
Step 4 tackles simultaneous versus separate requirements. Once your individual feature control frames are correct, you have to evaluate how they interact with each other. When you're looking at multiple single-segment FCFs or composite patterns on a complex drawing, the print must unambiguously specify how those multiple requirements interact. Do these two hole patterns need to be gauged simultaneously against the exact same datum setup, or can they be inspected separately?
If the drawing doesn't explicitly state the intent using terms like simrect or seprect, the manufacturer is left completely guessing.
Step 5 is our crucial reality check, the cost and capability sanity check.
You can have a flawlessly legal GD&T drawing that is absolutely impossible to manufacture affordably. As an auditor, you have to verify if any tolerance is obviously tighter than functionally needed. Is there a profile tolerance of 1/1000th of an inch on a bracket that literally just holds a plastic cover? Or is a tolerance tighter than your shop's machining process can actually hold without resorting to super expensive secondary grinding operations? This step ensures the print isn't just legally correct, but actually commercially viable.
Finally, we arrive at Step 6, the consistency check between the model and the print. In modern engineering, the 2D print is rarely the only source of truth. You have to query the model data. In model-based definition, dimensions that locate or orient may not even be visually shown. They're considered basic, and you have to query them from the 3D model. You must verify that the 3D model geometry, the physical part function, the related assembly drawings, and the 2D annotations are perfectly aligned. Are there missing basic dimensions? Does the model show a gap where the print implies a press fit? Step 6 is where you find those massive disconnects.
So, let's recap. Standards verified, datums selected, FCFs checked, requirements set, cost optimized, and consistency confirmed. By running this exact 6-step checklist, instead of just randomly scanning a document, you completely change your approach. You transform from a passive reviewer, hoping an error just jumps out at you, into an eagle-eyed master auditor who systematically dismantles a print.
Now that you have the framework, it's time to put it to the test. In our next capstone explainer, Lesson 12, we are going to do exactly that. We'll be doing a full, complex print critique and redesign on a flawed, real-world production drawing from start to finish. We're going to find the errors, explain why they fail, and fix them together. Until then, ask yourself, how much money is currently sitting on your company's shop floor being totally wasted by something as simple as a missing basic dimension? Think about it. I'll see you in the next explainer.
This is it, everyone, the absolute pinnacle of our journey. This is where everything from all 3 tiers of this masterclass finally comes together. You've powered through 35 rigorous lessons across the beginner, intermediate, and advanced levels. And today? Well, today you face the final boss. By the end of this explainer, you are going to critique a moderately complex production print with the exact same precision, authority, and foresight as a principal engineer. We're going to completely rip the drawing apart, find its hidden flaws, and rebuild it to a truly flawless standard. Let's get into it.
So, staring at a fully dimensioned, moderately complex production print can honestly feel completely overwhelming. I mean, we've got 14 complex feature control frames scattered all over the place. We're looking at multiple composite profile callouts, an intricate datum reference frame, a wild mix of maximum material condition and regardless of feature size modifiers, plus threaded hole projected tolerances. Staring at dozens of feature control frames all at once is enough to make anyone's head spin, even seasoned pros. But hey, we don't panic. We rely on our systems. Just like Lesson 11's checklist taught you, every single thing on a print branches from one core anchor, and that's the datum reference frame. So let's block out all the noise, zoom right in on the fundamentals, and start our audit right there. A DRF is a theoretically perfect XYZ coordinate system established by up to 3 datum features. It is literally the absolute foundation of your part's geometry because it constrains all 6 degrees of freedom, 3 translational and 3 rotational. If your DRF is flawed, every single tolerance that references it is totally compromised. To conquer this entire print, we're going to deconstruct and reconstruct it using our 6-step analytical framework. Audit the title and standard, audit datum precedents, decode the feature control frames, check simultaneous requirements, redesign for cost and function, and finally, verify internal consistency.
All right, diving right into steps 1 and 2, verifying the driving standard and the datum precedents.
The very first place we look is a title block. Our print here dictates the ASME Y14.5-2018 standard. Now that's a massive piece of intel because it means we absolutely must strictly abide by rule number 2. All geometric tolerances default to regardless of feature size, or RFS, unless explicitly modified otherwise. And the exact same rule applies to our datum feature references, which automatically default to regardless of material boundary. This seemingly innocent little default rule, it is going to become very, very important in just a few minutes. Moving over to the datums, we need to verify our precedents. Look at how our datums constrain this particular part. Our primary datum makes contact at a minimum of 3 points, establishing that first plane and stripping away 3 degrees of freedom right off the bat. Then, our secondary datum contacts at a minimum of 2 points, knocking out 2 more degrees.
Finally, our tertiary datum contacts at a minimum of 1 point, removing that last remaining degree of freedom. Boom, we have a fully locked rigid body. The foundation is rock solid. Before we move on to how this builds into the actual tolerances, I need you to stay super sharp. As we scan the rest of this print, there is one specific tolerance that, if left as originally specified, would have easily cost this program an estimated 5-figure sum in totally unnecessary inspection and scrapped parts. Keep your eyes peeled. Let's see if you can spot the trap before I point it out. Let's roll right into step 3, decoding the individual feature control frames.
Okay, here's your first applied exam question for the finale. We're looking at a positional tolerance applied to a threaded hole. I want you to pause for a second, look closely at this callout, and ask yourself what crucial symbol the original designer completely forgot to include. Think back to how fixed fasteners actually function in a real-world assembly.
If you just shouted projected tolerance zone at your screen, you absolutely nailed it. Exactly like we covered way back in Lesson 4. A standard position callout just isn't enough here. The thing is, a fixed fastener, like a stud or a screw, is entirely governed by the orientation of the produced threaded hole. If that hole goes in at an angle, the extended portion of the fastener acts exactly like a lever arm, multiplying that angular error as it goes up. We absolutely have to add a projected tolerance zone, that P inside a circle, along with a specified minimum height. That is the only way to guarantee the extended portion of the fastener won't interfere with the mating part. Let's get that redlined immediately.
Time for another rapid-fire check. We have 2 callouts pointing to different features here. A flatness callout referencing datum A, and a position callout referencing datum A. One of these is fundamentally breaking the laws of GD&T. Which one is it? If you caught the flatness error, phenomenal job. This perfectly illustrates a core ASME rule we explored during the beginner series. As this reference table confirms, form tolerances, which include straightness, flatness, circularity, and cylindricity, control a feature strictly relative to itself. They never, ever reference a datum reference frame. A surface is simply flat or it isn't, totally independent of the rest of the part. So we'll go ahead and strike datum A right out of that flatness callout. Moving into steps 4 and 5, this brings us face to face with that massive 5-figure tolerance trap I mentioned earlier. Do you remember rule number 2 from the title block? Because the original designer left a critical positional tolerance for a clearance hole pattern at the default regardless of feature size condition, they accidentally mandated incredibly strict, super expensive inspection criteria. Under RFS, the tolerance zone remains completely rigid and fixed regardless of how large or small the actual holes are machined within their limits. If a machinist drills the hole slightly larger, which by the way actually makes the mating pins fit easier, they get absolutely zero credit for it. This is exactly where you step in as the principal engineer. By deliberately adding the maximum material condition modifier, the M inside a circle, to the tolerance value, you completely flip the economics of this part. You unlock bonus tolerance. As the machined hole departs from its maximum material condition, meaning as the hole physically gets larger, the positional tolerance zone is allowed to grow by that exact same amount. This guarantees the parts will still perfectly assemble, but you just save the manufacturing floor immense time, money, and scrapped parts by giving them dynamic breathing room. It's a total game changer. Finally, step 6, ensuring internal consistency and tackling composite tolerancing. For our final check, we must carefully break down this highly complex composite feature control frame. We're looking at 2 distinct but heavily interrelated requirements inside a single rectangular box. The upper segment is the PLTZF, the Pattern Locating Tolerant Zone Framework. It has the larger tolerance and controls the location of the pattern as a whole group relative to the datums. The lower segment is the FRTZF, the Feature Relating Tolerance Zone Framework. This one is a much tighter tolerance that controls the size, form, and orientation of the features relative to each other. We've got to audit this lower segment, the FRTZF, against some very strict ASME rules. If datum references are repeated in the lower segment, they must be in the exact same order of precedence as the upper segment. But crucially, the datums in the lower segment only constrain rotation. They cannot constrain translation. So this means the tighter feature relating zone can literally float around, translating totally freely within the larger pattern locating zone, but its rotational orientation is strictly locked to those repeated datums. Our newly redlined print now reflects this logic perfectly. Just take a look at this beautiful side-by-side comparison. On the left is the messy, flawed, unnecessarily expensive original drawing. And on the right, that is your live, redlined, cost-optimized, functionally perfect redesign. Every single datum is justified.
Every modifier actually serves a purpose, and every composite frame is legally structured.
And that brings us to the principal engineer's verdict.
Think all the way back to the very first hook of the beginner series. I showed you how ambiguous, old-school plus-minus tolerancing could allow a part to pass every single dimension check on the inspection table, but completely fail to assemble out in the real world. Over these past 36 lessons, you have fundamentally transformed the way you view engineering drawings. You now possess the exact skills to design, specify, analyze, and audit tolerancing, so that a functional failure never, ever happens on your watch.
Your training here is technically complete, but your real-world application, that starts right now. I strongly encourage you to take this exact 6-step checklist, pull a real print off your own desk tomorrow morning, and audit it yourself. And hey, before you jump off, drop a comment below telling me your specific industry, whether you're in aerospace, automotive, medical device manufacturing, or consumer tech. I read them all, and I really want to know where you're taking these skills so we can dive into highly specialized applications in future explainers. As manufacturing technology advances, tolerances are only going to get tighter. Are your prints ready for the future? Keep engineering with precision, and I'll see you in the next one. Video title, GD&T Masterclass Finale, The Ultimate Print Audit. Thumbnail concepts. 1. The markup. A split screen showing a messy red-inked feature control frame on the left and a clean, green-checked FCF on the right. Big bold text overlay. Fix this print. 2. The 5-figure mistake. An extreme close-up of a standard feature control frame with a glowing red arrow pointing specifically to an empty space where an MMC modifier should be. Text overlay, $10,000 mistake. 3. Level 1 versus level 36. A side-by-side comparison. Left side says beginner with a simple plus dash dimension. Right side says principal engineer with a massive, complex composite profile feature control frame pulled from the ASME standard.
All right, let's just take a breath. You did it. I mean, 12 grueling lessons ago, you were simply applying GD&T. But now, just look at where you are. You've completely shifted gears from simple application into deep, rigorous, mathematical analysis. You can spot the difference between an ASME print and an ISO GPS print from a mile away. You're out here decoding complex composite profiles and pattern datums, navigating those tricky MMB and LMB boundaries. You're evaluating freeform profiles, balancing DFM cost trade-offs, and literally running Monte Carlo simulations to predict assembly failure rates. We absolutely didn't hold back, and, well, neither did you. Take a look at the core standard itself, ASME Y14.5. You aren't just staring at shapes and symbols on a piece of paper anymore. No way. You are actually reading the raw mathematical zone definitions. You're seeing the true geometric counterparts that a coordinate measuring machine actually uses to pass or fail a part. And honestly, the crucial takeaway is this number right here, 1%. That puts you in an exceptionally small, elite group of engineers. Because here's the reality. Most people who work with GD&T never, ever go this deep. They just kind of blindly apply the standard. But as this says so perfectly, you no longer just apply, you audit. You can now analyze the standard, question it, simulate it, and audit it at a level that, quite frankly, most of the industry doesn't even operate at. But there is one more tier. The expert and mastery tier is coming soon. And listen, this isn't about learning more obscure symbols or doing even harder math. It's a totally different kind of tier. It's about authority. It's about nailing your GD&T certification, building those company-wide standards, leading major design reviews, and really becoming the person your organization actually trusts to own this whole process. That is the true final step. But before we get there, I really want to hear from you. Drop a comment right now and let me know which part of this advanced tier hit hardest for you. Seriously, your feedback directly helps us decide what gets covered in even more depth when we officially launch Expert and Mastery. So make sure to hit subscribe so you absolutely do not miss it when it drops. And hey, if you just skipped ahead to see what the peak of the mountain looked like, don't worry, the beginner and intermediate masterclasses are linked right down below to get you started on the climb. You have officially earned this technical mastery. Now, let's get ready to lead.